today I want to talk about graphics virtualization by using virglrenderer. To do so, I will follow the points I will lay out here on this slide. First, I will give you a bit of history, then I will give a design overview, how it is done when we get up to OpenGL 4.3. I will talk about the life of a buffer and how draw calls are done. Then I will go into the advantages and disadvantages of this approach and talk a bit about block resources in Vulkan. And finally, I will go into future directions that this project is taking. The project was started by Dave Arley in 2014 as a research project, and initially it only supported Chemo. In 2017, Collabora and the Chromium team of Google started to contribute, added support in cross-VM, and worked toward getting conformance for GL ES in the guest application. All in all, the work so far reached a level of support of OpenGL 4.3 and OpenGL ES 3.2 in the guest if the host supports sufficient features. In 2018, Virtual was enabled for the Linux development virtual machine that is delivered with Chrome OS. And as of now, Chromebooks are shipping that have this development virtual machine enabled and installable, and you get in there OpenGL accelerated by Virtual. Now let's have a look at the design of virglrenderer if we have support for OpenGL up to 4.3 in the guest. Here you can see in this diagram that this virglrenderer is actually composed of two parts. There's on one hand the virtual driver which lives inside Mesa and is run in the guest, and there's virglrenderer, a library that runs on the host. Now, if a guest application wants to do OpenGL, it uses Mesa as an OpenGL implementation. It calls into Mesa, and there Mesa translates the OpenGL calls to Gallium calls, which is the generic driver framework in Mesa, and then Virtual as a specific driver receives the data and the calls from Gallium, and then encodes everything into the command stream and requests resources from the host by means of the Windows System Integration layer. These requests are sent to the guest libdrm and kernel, and then the virtual machine forwards the calls to the host virglrenderer, and here the command stream is decoded, the resources are managed on the host, and everything is encoded again or translated again into OpenGL calls that are then called or executed by the OpenGL driver on the host. Finally, if there's something to be drawn, everything will be drawn on the output surface that was requested by the virtual machine from the host driver. So now let's have a look at what happens when we want to use a buffer, which is kind of a common thing. So the guest is calling GL buffer, GL bind buffer, then GL buffer storage, at which point Mesa and Gallium calls the method create resource, which is forwarded to the virtual driver and then to the virtual Windows System Integration. Here, a handle is assigned to the resource, memory is allocated to schedule the data on the guest side, and a call is issued to the DRM layer to create the resource on the host. Now, when the host receives this command, it again calls GL buffer, GL bind buffer, GL buffer storage, but this time, of course, on the host. And after all this is finished, the handle is associated with the buffer so that in the future we can actually find out which buffer we actually want to use when the guest wants to use a certain buffer by means of the handle. Now, if we want to update the data in the buffer, we have to map it and unmap it in a read-only fashion. In this case, the guest is calling GL map buffer with write-only flag set, and then virglrenderer is looking, is this resource actually in use right by the host still? If it is in use, then it will create a new resource, flush the old one, but return the pointer to the new resource memory to the guest. If the old resource is no longer in use, we can just pass the pointer of the old resource to the guest. Then the application writes the data to this memory, unmaps the buffer by calling GL unmap buffer, and then virtual sends the transfer to the transfer queue, and eventually there will be coming a flush that flushes the command stream, and this command will be sent to the host. When the host receives the transfer command, the buffer is mapped, the data inside the buffer is updated by the data that was received from the guest, and then the buffer is unmapped again. So it's straightforward. Now, if you want to read something back from the host, like for instance a query result, the algorithm is like this. The guest calls GL map buffer, in this case with the read-only flag set, for instance. We don't want to talk about read-write at this point for simplicity. Then virtual sends a read transfer command and flushes the command stream. And then it waits for the host to finish. The host receives the transfer command, it flushes the commands on the host side, and then it waits for the OpenGL implementation to finish. And when this is done, it maps the buffer, it copies the data onto the transfer object from the buffer, and then it unmaps the buffer again. And then it signals the guest that the guest can continue. At this point, the guest returns the pointer to the updated shadow memory back to the application, and the application can read back the data it wanted to read. And finally, the guest application calls GL unmap buffer, and nothing further is to be done. What is kind of hidden and not talked about here is how the host is actually copying the data to guest memory. Usually it's done in the kernel. It's an extra copy that you have to live with. Now if you want to draw something, how this is done? Well, essentially the guest emits buffers and states, and all this is encoded in the command stream, and at one point it will issue a draw VPO command, and then it will continue emitting buffers, emitting states and stuff, emitting textures, and again calling draw VPO and so on until for some reason the command stream is flushed. This can be either because the command stream is full and we need to flush it to be able to add more commands, or because we want to read something back. Now, at this point, the host receives the command buffer and it executes the command. It decodes the commands, it executes each command one by one. It updates the host state values, but doesn't send anything to the hardware yet, because we don't want to update things that don't need to be updated all the time. It may be that the same state is sent again, but with a different value, and there's no need to send it to the hardware. Then when the draw VPO command comes, we actually set the states in the hardware. We select shaders, variants are created and linked, and then the draw command is issued on the host. When you look at this diagram here, or this picture, you see actually kind of what is happening on guest and host side, more or less synchronously. On the upper line you see EGL trace, which means we have an API trace which is replayed in the guest, and you see the lines that indicate OpenGL commands, and the white space between this is what API trace is doing to decode these commands from its file. And then in the lower part you see what's happening on the host. So there's this big process command batch, and inside there the command submit 3D, and then you see all the little commands and functions that are executed on the host. There's a lot of things that go on in virglrenderer itself, but also a lot of OpenGL calls. In summary, when you translate something that's running in the guest to the host, it often happens that on the host it's running a lot more commands than it's running in the guest. One example is the way how a clear command is executed. GL clear, when it is issued on the host for the full frame buffer, then only in that case the gallium command clear is sent. In all other cases we draw some rectangle. Now in this case, the clear command says I ignore every other state, but it's actually not flushed to the driver. So in this case the host knows when I get this command I have to clear everything that has to do with scissors, that has to do with color, masks. Then I have to do the clear, the GL clear, and then I have to reset everything, because the guest never told me how the states should be before the clear and afterwards, so I have to recreate the state that was before the clear, which makes a simple clear a rather large series of commands on the host. Which brings us to the disadvantage of this approach for virtualization. The first thing is, of course, as you might already have guessed, data is copied multiple times. The first line here is what is done in any case. The Mesa client sends the data to Gallium and to the driver. The driver sends it to some DRM buffer to the hardware. But in this case, the hardware is actually another computer, the host machine. So in the kernel, data is sent to the host memory. VirGL may need to transform the data again. For instance, if we receive the data in chunks, it has to put them together again. And then the host driver will do more copying. Imagine, for instance, the host driver is also Mesa. In Mesa implemented, then we have exactly what's happening in the first line. The Mesa client sends data to the Gallium driver, then the driver, which in this case will probably be something else than virtual, sends the data to the DRM buffer to the hardware. So there's at least twice the amount of data moved around, even more. The next thing is all OpenGL states need to be encoded, then decoded, and then recreated again on the host as OpenGL calls. When you look at shaders, for instance, so the guest compiles and links the GLSL to TGSI ER that is transferred to the host. The host creates a new GLSL shader that represents what's done in the TGSI. It may have to create variants at link time based on the rasterization state, for instance, to emulate features that the host doesn't support, but that we want to support in the guest. It happens a lot when we run an OpenGL context in the guest, but have only OpenGL ES context on the host. And then the host driver compiles and links the shaders again. Now, the next problematic thing is that host virglrenderer runs in a single process, which means specifically decoding the command stream of multiple apps are all handled in one thread. It means if you have more than one OpenGL app running in the guest, you have to share one command stream, one command queue, and the neat result is if you run, for instance, GLX gears, one instance, and you get 1000 frames per second. Then when you run two instances in the same virtual machine, you will get 2 times 500 frames per second. When you run 3 times GLX gears, you get 333 3 times, all the 3 instances, and so on. So the design that we currently have is not ready for more than one application, OpenGL application in the guest. And finally, losing the host context is not handled gracefully, which means you cannot migrate the virtual machine with a running 3D application to a different host without losing the 3D application. Now, there are of course advantages, otherwise you wouldn't do this. The first thing is the virtualization is pure software, which means the guest driver is completely generic. It doesn't need to know anything hardware specific in the sense that you would need to know where buffers, addresses and stuff are. Everything that the guest needs to know about the host can be queried by OpenGL commands, like querying the version of OpenGL and querying the extensions that the driver supports. And based on this, the host version and the extensions that the host driver supports, the guest OpenGL exposes a certain version of OpenGL. Usually it maps 1-to-1. You have a certain version on the host, like 4.2, you get 4.2 in the guest. You have OpenGL ES 3.1 in the host, you get OpenGL 3.1 ES in the guest. Of course, only up to 4.3 at this point. Now, with that, you can also emulate OpenGL in the guest if you have only a GLES host. Many features that are missing in GLES can be emulated, like rectangular texture and logic ops you can all do in the shaders. So you can tell the guest OpenGL is available. There are certain things that cannot be emulated, like OpenGL requires that you have 4 streams in geometry shaders, but GLES only has usually 1. Requires only 1 and only supports 1, so this cannot be emulated. Anyway, doing this OpenGL on top of GLES is currently done in the code books. And you can actually play some games if you want to. Like Portal 2 or something, old games mostly, but also something like Alien Isolation works on GL ES host implementation, even though it requires something like OpenGL 4.3, I think. Okay, the next thing is, of course, since you run on any host driver without specifics, we can run on a software driver, which is nice for running virglrenderer and testing virglrenderer in the CI. And this is actually done in the virglrenderer CI and also in the Mesa CI. And finally, without blob resources, the guest is completely sandboxed. So no copying of guest data directly to host memory or reading from the host memory to guest is possible. The thing is, of course, we really want blob resources because we want OpenGL 4.4 and more, and we want Vulkan, and these need to map buffers directly from the host in a coherent and persistent way. So in this case, the implementation that is now done and is already working in CrossVM and currently in the works for QEMU is using file descriptors to share resources between host and guest. And the host resource is then mapped directly into the guest PCI address space so that the host GPU memory can be directly mapped inside the guest, and therefore zero copy between the guest application and the host GPU memory becomes possible, which is good for performance, but maybe not so good for security. That depends on how good the implementation is. Now, if you look at OpenGL 4.4, in the diagram we had before, there is this blob resource that is newly introduced, which is managed on the host and referenced to also the guest. And you see this red arrow from the guest application to the OpenGL driver, which means copying between host memory and guest, host GPU memory and guest is possible. Now with blob resources, Vulkan becomes actually possible. And Vulkan makes things a lot simpler than OpenGL. Host resources are mapped directly, so there's always zero copy. Most state information is just forwarded, so there's no or less, a lot less re-encoding. Shaders can, for instance, be passed as SPIR-V, so it's all a more direct approach than the OpenGL, what I was talking about. On the other hand, while this Vulkan implementation is still work in progress, it already works somewhat with CrossVM, but it's not that performant. And, well, it's a very active project at the moment, so stay tuned for new things there. Now, where do we go from here? Well, of course, we always look into performance optimization. One thing that comes to mind is always a better synchronization between host and guest. So on one hand, that the host doesn't starve, doesn't have to wait for the guest to send more data and more commands. On the other hand, the guest shouldn't wait too long for host responses. The next thing is we think about exploiting zero copy even in OpenGL contexts that are lower, like OpenGL 4.3, 4.2, where we map buffers non-coherently and non-persistent, but kind of think about using blob resources to do this in the background to avoid the copying that is currently done all over the place. Then we think about using Zink, the OpenGL over Vulkan layer, to replace virtual because of the direct nature of Vulkan. This might improve OpenGL performance, but Zink, just as Vulkan in virglrenderer, is currently a project that is still quite young and is still moving forward, so we cannot say where this will lead us. And finally, we think about multiprocess support to get around this bottleneck when decoding the command stream, so that actually running more than one application, more than one OpenGL application in the guest becomes survivable. Okay, that's all from my side. Thank you for listening and watching this video, and I'm here for your questions.